Hello students. So today I will be talking about band gap engineering. Now we will use this band gap engineering to construct optical devices or electro-optical devices or optoelectronic devices, as you can say it. Now let us first start with what we usually have as a conventional transistor. Now in a conventional transistor, we know that we have emitter, base and collector. Now this base in a conventional transistor, it has got a uniform energy gap. Uniform energy gap or band gap, whatever you can call it. But it has got no electric field. Therefore, electrons are unable to traverse through the base. In the base. By relatively slow diffusion process. Now, one way to speed up the process, so need to speed up. One way to do it is to gradually change the base composition. Gradual change of base composition. And what it will do, it will lead to a conduction band to tilt. A tilting of conduction band will take place, and this conduction band tilt usually takes place when electric field is present, so it will be equivalent to an electric field being present. And hence the electrons can do a fast drift. So what we will focus now is, so if we change the composition of the base, it will simply look like this. This happens to be the base. This is the collector. And this is the emitter. So what we have is a graded band gap bipolar transistor. Now what happens here is the current injected in the base controls electron flow from emitter to collector. So let me write this one also. So current, it's a different color. Current injected in the base will control the electron flow from emitter to collector. This is the advantage of having this graded band gap bipolar transistor. Another optical device based upon band gap engineering. So what we have done is a band gap engineering. So another optical device based upon band gap engineering is the Avalanche photodiode. It is basically a P injection diode used to convert light into electrical signal. So light gets converted to electricity. Let us put it as electrical signal to be precise. Now this response of this avalanche photodiode, this can be enhanced by something called multi-well quantum structures. Multi-well quantum structures. That means we have a series of conduction band and valence band. So this is basically called a super lattice. It's called the super lattice array, where we create the material such that there is a conduction and a valence band like this. Now in case of an avalanche photodiode, it looks something like this. This difference, this is your conduction band, so this is, we can put it as delta EC. Now due to this band gap engineering, there is a slight deviation in the conjugate band. It is not used to be like this, so there is a small deviation, so that we can call it as delta EC, and this is your change in valence band position, so we can call it as delta EV. So we have delta EC, change in energy level of conduction band, and delta EV, change in energy level of band gap valence band, and all of them have been possible due to this graded doping, or this is actually called band gap engineering. Now when a photon hits, the electrons will flow in this direction and the holes will flow in this direction. Now what happens is that these electrons, they get energized due to this difference in energy level, and that means due to delta EC. And as they got energized, they ionize the lattice atoms. And in turn, more carriers are generated. So basically, that is why it's called an avalanche. So one single electron or some few electrons, when they accelerated, they create more carriers, and those more carriers will create further carriers, so on and so forth.